All right, in this video, we are going to discuss the properties of radicals. Radicals are the same thing as roots. So we're going to talk about roots and radical notation. We're going to talk about simplifying radical expressions, combining radical expressions, and using rational number exponents. So let's start with square roots. For any real number a and b, if a squared is equal to b, then the absolute value of a is what we call the square root of b. In other words, absolute value of a is square root b. So this little squiggly sign is indicates a square root. If we don't specify, it means a square root, or we can put a tiny number inside that little nook, and that's going to tell us the index of the root. So we can do a cube root, a fourth root. We can really do any number of roots, okay? But the default is a square root. So for example, the square root of 9 is 3, and that is because 3 squared is equal to 9. These square roots are really just a way to reverse exponents. We could also say the square root of 0.0025 is 0.05 because 0.05 squared is 0.0025. All right. We could say the square root of 25 over 10,000 is 5 over 100 for the exact same reason. All right. We can say the square root of 36 times x to the 14th is going to be 6x to the 7. And that's because 6x to the 7 squared gives us 36x to the 14th. Take a look to the right, see how 6x to the 7 squared is 6x to the 7 times 6x to the 7. And when we combine that, we get 6 times 6 is 36, x to the 7th times x to the 7th is x to the 14th. Okay. So take a look at this one, make sure you understand that. If not, pause it and try to work through it. Those are square roots. Now let's talk about cube roots. Definition of a cube root is that for any real numbers, a and b, the cube root of b is a, if and only if a cubed is b, okay? So the cube root of b is a, if a cubed is b. Notice here we don't need those absolute value bars, and that is because if our a is a negative number, then when we cube it, we also get a negative number. So cube roots, it's fine for our radicand to be negative, whereas square roots, it is not. Okay. On the left, you see some examples of cube roots. Cube roots of 8 is 2. Cube root of 27 is 3. Cube root of 64 is 4. And the cube root of 125 is 5. These are just good numbers to remember that they are perfect cubes because they really just come from 2 cubed, 3 cubed, 4 cubed, 5 cubed. Okay. Like I said before, since a negative number multiplied 3 times is still a negative number, we can take cube roots of negative numbers. So here, the cube root of negative 125x to the 6th is going to be negative 5x squared. Because remember, we're taking basically a third of these factors. So a third of 6 factors of x is going to be 2 factors of x. Okay. Now we can talk about nth roots. So nth roots, I mean a 4th root, a 5th root, basically any positive, real number, real integer, we can take a root of. We can use as an index in our roots. So the definition of nth roots is for any real numbers, a and b. The nth root of b is a, if and only if a to the nth power is also b. Okay. So it's really the same definition. Here we can take something like a 5th root. So the fifth root of negative 32 is going to be negative 2. And that's because negative 2 to the 5 is negative 32. Okay. But we can't take the fourth root of something like negative 16 because there is no number that when raised to the fourth power is going to give you a negative number, right? Any even powers will always have positive results. So we can't take an even root of a negative number, right? So I'm saying is if the index of the root is even, then the radicand to be either a 0 or a positive number in order for this root to be a real number. So let's talk about how we simplify radicals. Radicals follow the same properties as exponents because I'm going to show you later they really are exponents, okay? So we have the product property, which tells us that if we have the product of two numbers inside a square root, we convert that to the product of each of those numbers square rooted. And we also have the quotient, which allows us to distribute that radical over the quotient, okay? And we can deal with the numerator and the denominator separately. All right, so what does it mean to simplify radicals? Well, an nth root is in its simplest form when the radicand, which is the stuff inside the root, has no perfect nth power as a factor, okay? If the index of the root is an even number, then the radicand needs to be non-negative for the root to exist. Keep that in mind. And then just notice kind of what we're talking about here is that down here, you see if we've got n powers of x and we want to take the nth root, then we're just going to have 1 power of x left. Okay. So here's some examples I'm going to go through with you guys. If you feel like you understand this, you might want to pause the video here and work through these examples on your own, okay? Work through the examples on your own, get all 6 of them complete, and then watch the video to see if you got the same answers as I did, okay? So let me share my whiteboard with you, and we'll get started. All right, so our first example is going to be the square root of 12. And if we want to simplify this, what we want to do is remove any perfect nth powers. Since our the power or the radical is a square root, we need to remove any perfect powers of 2. So the first step is going to be to factor this guy. 12 is 2 times 2 times 3, right? And you can see there we have 2 powers of 2. So we've got a 2 squared inside of our square root. All right. So if we have a square root and a 2 squared, we can take that 2 squared out, or essentially take the square root of 2 squared. So we can use that, that product property and separate these two guys, and then you'll see that the square root of 2 squared is just going to be 2. But we still are going to multiply it by the square root of 3 because we cannot take the square root of 3, right? So our square root of 12 becomes 2 square root 3. Let's go on to our next problem is the square root of 5x to the 4th over 9. All right. So we can use our properties to break this up into a 5x to the 4th over square root of 5x to the 4th over square root of 9. And we know that the square root of 9 is just 3 because 3 squared is 9. Conversely, we could also say that instead of thinking about this 9 as a 9, we can think about 9 as 3 squared, and we're taking the square root of 3 squared. Okay. Now in the numerator, we've got the square root of 5 times the square root of x to the 4th. Well, x to the 4th is really like x squared times x squared. So if we want, we can write that as the square root of 5 times the square root of x squared times the square root of x squared. Well, the square root of x squared is just x. So we've got square root of 5 times x all over 3. And to avoid any confusion about where this radical ends, we usually like to write everything before the radical. So I'm going to put my factors of x before that root 5. Right. And now that radical is completely simplified. Our next example is the square root of 72. Sorry, negative square root of 72. Since the negative sign is outside of the root, that's fine. That negative sign is just going to carry through into our final answer. All right. Now we need to see if we have any repeat factors. So any factors that occur twice, we can take a square root of them. Okay. So this is 9 times 8. And 9 is 3 squared, and 8 is 2 times 2 times 2, or we could call it 2 squared times 2. So I specifically wrote out our factors in groups of 2 so that we could take our square root. Okay. We can take the square root of 3 squared, we can take the square root of 2 squared. And we are going to get a 3 times a 2, but that last 2 is still stuck inside. 3 times 2 is just 6, so we end up with negative 6 times the square root of 2. And the radical is simplified. Our next one, we're actually going to take a third root. So we are going to look for factors that repeat 3 times. And so when I factor my numerator and denominator, I'm going to put any factors that occur at least 3 times into groups of 3. So we can also remember, split the radicals over the numerator and the denominator. Okay. Now in the top, I've got x to the 6, but that's the same thing as x to the 3rd times x to the 3rd. And I've got z to the 4th, but that's the same thing as z to the 3rd times z. Okay. And in the bottom, I have 27, which is the same thing as 3 to the 3rd. So now I can take the cube root of x to the 3rd is just x, the cube root of x to the 3rd is just x, and the cube root of z to the 3rd is z. And we still have our last z stuck inside that cube root. Okay. And then in the denominator, we've just got a 3. So overall, we've got x squared z root z all over 3. And that is this radical simplified. Okay. Next example is going to be another third root of negative 125. Here our negative sign is inside the radical, but that's okay because we have a, the index of our radical is an odd number. Okay, so it's okay that we have negatives inside. So we just need to figure out if we have any repeat factors here. 125 is actually negative 5 to the 3rd. So we've got the third root of negative 5 to the 3rd. So this answer is just negative 5. And for our last example, we've got the square root of 32x to the 11th. And we'll do just what we did before. We'll break this down into factor pairs of 2. So 32 is going to be 2 squared times 2 squared times, let's see, is it just times 2 one more time? So 2 times 2 is 4 times 4 times 2. Yeah, so 32 is 2 squared times 2 squared times 2. And x to the 11th is going to have 5 of these x squareds and then a single x. Okay, so when we break these guys out, we're going to have 2 2s, which is 4, and then we're going to have 5 of these x's, but then the remaining 2 and x are stuck inside that radical. All right, now let's move on to rational exponents. Keep in mind, an exponent tells us how many times to multiply by the base, and a negative exponent tells us how many times to divide by the base. So a rational or fractional exponent tells us to multiply a fraction of a number of times by the base. This is similar to a radical. We've got 2 to the third means 2 times 2 times 2. To the negative third means 1 over 2 times 2 times 2. All right, so we've got that our cube root of 8 is 2. What that also could mean is that since if we have 8 raised to the 1/3 power, we are saying multiply by 8 1/3 of its factors times. Okay, well, since 8 is composed of 3 factors of 2, 1/3 of those factors is going to be just a single factor of 2. So the cube root of 8 and 8 to the 1/3 power is the same thing. Okay, take a minute to understand how that works. So basically, the denominator of a fractional exponent is the index of the radical. All right, so we have all the exponent rules that we've gone over before, and we just want to add this new exponent rule regarding our fractional exponents. So when we have a fractional exponent x over y, the numerator of that fractional exponent is still an exponent, but the denominator of that exponent can be translated as the index of a radical. Okay. If our numerator is just 1, then that fractional exponent really just is a radical. If our numerator is something else, then that fractional exponent is a radical and a power. Notice when you translate into the radicals, the order does not matter. Now, keep in mind, knowing this, that we can translate between radicals and exponents, means that whenever we have radicals, we can translate to exponents and use all the exponent properties. Okay. So let's look at a couple examples here. 4 to the 1/2 power is the same thing as the square root of 4. 4 to the 2/3 power is the third root of 4 squared. Okay. That is how rational exponents work. Right. So here are the translations of our rational exponents. All right. If our denominator is something, that becomes the index of our radical. If we have a numerator and a denominator of our exponent, then we've got an index of our radical and an exponent. And if we've got a negative number, remember that puts us dividing that fraction of a number of times. And it can also be dividing by a radical. So let's do just a couple examples here. to simplify and rewrite these expressions without any fractional or negative exponents. Okay, I've worked out the first two already. 4 to the 1/2 is the square root of 4 is 2. 4 to the 2/3 is the third root of 4 squared, which gives us 2 and the third root of 2. Okay, now I'm going to go through these next 4 examples on the whiteboard. If you feel like you understand this, you might want to try, and even if you don't, you might want to try working through these 4 examples on your own and then coming back to this video to compare with my answers. So our first example is -64 to the 1/2 power. Remember, that negative sign is not being raised to the 1/2 power because there are no parentheses including it. We can translate this to be negative the square root of 64. And now let's factor 64. 64 is actually 2 to the 6th power, or we can write it like this. 2 squared times 2 squared times 2 squared. So when this all comes out, we still have that negative sign, and we have 2 times 2 times 2, which is 8. Okay. Or if you wanted to factor it differently, you could say the square root of 64 is 8 because 8 squared is 64. That negative sign is just a factor of -1 that is outside of the radical that we carry through to the end. Let's look at our next example. It is 3x to the 1/2. Again, that 3 is not part of the radical, okay? So this just becomes 3 to the square root of x, right? And that's just a different way to write it. We cannot simplify this anymore, but we have now written it without fractional or negative exponents. And let's go on to the next example, 9/25 to the 2/3. All right, so that 2 in the numerator of our exponent stays as an exponent. That 3 in the denominator is our radical. So we are taking the cube root of 9/25 squared. Right, that's how that translates. Now, before we take that cube root, let's just look at what we've got. 9 is 3 times 3, and 9 squared is going to be 3 times 3 times 3 times 3. 25 is 5 times 5. 25 squared is going to be 5 times 5 times 5 times 5. We are looking for 3 repeat factors to take the third root of. So we can take out these 3 repeat factors and take their third root. It just becomes 3/5. And then we've still got the third root of the remaining 3/5. All right, so that is our third example. And then our final example, -27 to the -2/3 power. Now here we've got parentheses around our -27, which means that that negative is included under the radical. So again, we are taking the third root of -27. And then that whole thing is being squared. And because we have the negative sign here, this entire thing is going to be under 1. So the third root of -27 is going to be -3. So we've got 1/3 squared, and -3 squared is a +9. So we end up with 1/9. Okay. One way to look at this is 27 is 3 times 3 times 3. We are taking 2/3 of its factors. So we're taking just the 3 times 3, and we're getting our 1/9. Okay. So let's go back over the relationship between rational exponents and radicals. Because rational exponents essentially are radicals, we have some of the same properties. We still have our product property for our radicals and our quotient property for our radicals, just like we did for exponents. Really, the properties of radicals and rational exponents are redundant when we understand the connection between the two. So when you look at the property, an nth root of a product is really just that product to the power of 1 over n, which we know we can distribute because we know the powers of our exponents, or we know the properties of our exponents, okay? Same thing with the quotient rule. If you turn that radical into an exponent, then you can just apply the exponent properties, and you don't have to memorize 2 sets of properties, one for exponents and one for radicals. They're the same thing. So how do we add, subtract, and multiply radical expressions? Well, when it comes to adding and subtracting radical expressions, only radicals with the same index and same radicand can be combined. These are what we call like radicals. We can add like radicals in the same way we add like terms, which is by using the distributive property in reverse. So just like 2x and 5x are like terms because the x's are identical, and we have 2 of them and we have 5 of them, we just add them together, we've got 7 of these things. Radicals are the same. If we have 2 root 3 plus 5 root 3, then we've got in total 7 of these root 3s. Something that is not a like radical that cannot be combined would be like a root 5 and a cube root of 5. Since the indexes are different, we cannot combine them. They are not like terms. Let me do these 2 examples for you to show you how to add and subtract radical expressions. It does involve doing some simplifying steps in between. If you think you know how to add and subtract these expressions, go ahead, pause the video here and work through them on your own and then come back. Our first example is the cube root of 24 minus 4 times the cube root of 81 plus the cube root of 3. At first glance, these do not look like radicals, but we should probably simplify each of them first just to see. 24, let's factor 24 is going to be 2 times 2 times 2 times 2. Oh, excuse me, I think I have one extra 2 there. Yeah. 24 is 2 times 2 times 2 times 3. Right. So you can see right away we've got 3 factors of 2 and we are under a cube root. So that is going to simplify to 2 root 3. Right. Now let's take a look at our 4 cube root 81. Well, 81 is going to be 3 times 3 times 3 times 3. And again, we've got those 3 factors of 3 that we can pull out. So we've got 4 times 3, but that last 3 is still stuck under the cube root. Okay. Now we've just got this cube root of 3, which we cannot simplify. So you see, we've got 2 of these cube roots of 3. We've got 12 of these cube roots of 3, and we have 1 of these cube roots of 3. These actually are all like terms. So we've got 2 minus 12 plus 1 of these cube roots of 3. And that is going to give us -9 cube root of 3. So even though it didn't look like we could combine these terms initially, you have to simplify completely first in order to see if you actually have like radicals or not. Let's go on to the next problem. So our next problem is going to be the cube root of 6y over 125 plus 3 times the cube root of 6y, right? Well, our 125 can come out of the cube root because 125 is 5 to the third. So we are going to get the cube root of 6y all over 5 plus 3 times the cube root of 6y. We're adding these guys together. The radical parts are the same. But what exactly are we adding together? We've got 1/5 of these 6y's plus 3 of these 6y's, of these cube root 6y's. All right. So this piece right here, this cube root 6y over 5, that's really 1/5 of these cube root of 6y's. So we can undistribute like this, and we're going to get 3 and 1/5 6y, or if we want to write it in fractions, we've got 16 over 5 of these cube roots of 6y. Right. So again, you want to make sure that you are simplifying your radicals before trying to add or subtract them. So we've added and subtracted our radicals. Now let's work on multiplying some radical. When we multiply radical expressions, we just multiply them as if they are normal expressions, and then use our properties of radicals and of exponents to simplify them as necessary. So I've got 4 examples here that we will work through on the whiteboard. Again, if you feel comfortable, go ahead and try to work on these on your own, and then come back to the video. For our first example, we've got root 5 minus root 6, all multiplied by root 7 plus 1. We're just going to use FOIL or the distributive property to multiply all of this stuff out. So we've got root 5 times root 7 and root 5 times 1. And then we've got a negative root 6 times root 7, and we've got a negative root 6 times 1. Okay. Then we can use our properties of radicals to put these under the same radical. Right. And if you want, you can multiply that out. We've got 4 unlike radicals, and there is nothing we can do to simplify here. Let's go to our second example, which is a little more interesting. We've got square root of 2x minus 5 times the square root of 2x plus 5. And you're going to notice that these two pairs have a special relationship, being that the only difference is that the first two are being added, or the first two are being subtracted, the second two are being added. So again, we're going to use that distributive property. We've got root 2x times root 2x, and then we've got 5 times root 2x, and then we've got negative 5 times root 2x, and then we've got negative 5 times 5, which is going to be negative 25. All right, so we've got these 4 terms, and conveniently enough, this is a negative term, that's a positive term. They're going to cancel out. And then if you notice, we have root 2x squared. So that essentially simplifies to just a 2x minus 25. Okay. So that is example 2. Let's go on to example 3. We've got the cube root of 2 multiplied by the cube root of 4 plus 1. We'll distribute this cube root of 2. So we've got the cube root of 2 times the cube root of 4 plus the cube root of 2 times 1. Now we'll combine these two cube roots. We've got 2 times 4, which is 8. And we know that the cube root of 8 is actually just 2. So we end up with 2 plus cube root of 2. And that is that third problem multiplied out and simplified. Right. We've got one more. Here we've got the square root of x plus 2 being added to 3, and then the whole thing is being squared. You want to be very careful here. Because we have addition, we cannot distribute this exponent over the parentheses. Okay, what we have here is the square root of x plus 2 plus 3 times the square root of x plus 2 plus 3. We have to use FOIL again, or the distributive property, to multiply this all out. Okay. And in the end, we are going to get x plus 2. It's going to be what we get when we do square root of x plus 2 times square root of x plus 2. And then we're going to get 2 of these 3 times the square root of x plus 2. So these are going to be, this term is the same as that term. So that's why I've got 2 of them. And then we've got our 3 times 3, which is going to be a 9. Okay. So this can all simplify to be x plus 11 plus 6 root x plus 2. All right, and if you want to walk through that on your own a little slower, doing each of the FOIL steps, you can do that. I did jump a few steps there. All right, so that is multiplying our radical expressions. All right, the very topic cover in this section is going to be rationalizing the denominator usually or the numerator of a fraction. So to rationalize means to get rid of the radical. So maybe basically get rid of the root, and we can only do it in one piece or the other of our fraction without actually changing the value of our fraction. So in this example, I'm going to show you how to rationalize the denominator, which means we're going to get rid of the radical in the denominator of these fractions. So we're going to rewrite them as equivalent fractions without radicals in the denominator. And as you probably remember, to make equivalent fractions, we multiply by versions of 1. We're going to use a strategic version of 1. That is going to give us the necessary factors to complete the radical. So if it's a square root, we need to make sure that all the factors inside that square root have pairs. If it's cube root, we need to make sure that all the factors inside that cube root come in groups of 3. Okay. So in this case, we've got 2 root 5. If we want to get rid of the radical in the denominator of this fraction, we're going to multiply it by root 5 over root 5. And that's because square root of 5 times square root of 5 is going to give us just a regular 5. Now over here, we've got the 7 over the cube root of 2. If we want the cube root of 2 to turn into a non-radical, then we're going to need 3 factors of this cube root of 2. So we're going to multiply it by the cube root of 4. So now when you combine that denominator, you see the cube root of 2 times the cube root of 4 is going to give you the cube root of 8, and the cube root of 8 is 2. Let me do a couple more examples on the whiteboard for you so you can see how these guys work. So if we want to rationalize the denominator of this first example, we don't have to worry about it. We just have to worry about this square root of x. Since we have a single factor of x, square root, we're going to need another factor of square root of x to turn this into a equal fraction, because this is just 1 that we're multiplying by, but it ends up looking different in that the denominator no longer has a fraction in it. That root x times root x is just going to give us ax. So now we've made an equivalent fraction that does not have a radical in the denominator. That is rationalizing the denominator. Let's do one more example. And I'm going to actually change it from the example you saw in the PowerPoint. Let's do this one. All right, so there is a radical in the denominator here because the numerator and the denominator are both under a radical. Now we know the cube root of 1 is just 1, so we don't need to write the radical in the numerator actually. Now, if we want to find something that we can multiply the cube root of 25 by to turn it into a non-radical, we have to realize that 25 is 5 times 5. So we only need one more factor of 5 to turn this denominator into a non-radical number. So we've got 3 times 25 times 5, but 25 times 5 is just 5 to the third. So we've got the third root of 5 over 5. And that is our fraction that is equivalent to our original fraction. It just doesn't have a radical in the denominator. All right, let's go over rationalizing the denominator when we have two terms in the denominator. It is a little more complicated here. If you see from our example, if we are to multiply this fraction by root 2 over root 2, then when we distribute that root 2 out, it actually doesn't disappear. It'll become a new term with a root 2. So here we have to use what we call conjugates. Conjugates are the sum and the difference of two terms. I think we actually saw an example earlier where I multiplied the sum and the difference of two terms, and you saw that we lost all our radicals. So a plus b and a minus are conjugates because one is a sum and one is a difference. When you multiply a plus b times a minus b, the cross terms, the b times a and the a times negative b, cancel out, and you just a squared minus b squared. All right, so it's nice because you just end up with squared terms, which means we can get rid of any square roots that we want to. So since we have two terms here, 3 root 2 plus 4, we're going to have to multiply by the conjugate, 3 root 2 minus 4. Okay. Keep in mind, when you multiply all this stuff out, you need to put parentheses around because our fraction bars are grouping symbols, and use the distributive property. Okay. Here we end up with just a 3 root 2 minus 4. Make sure you take some time to work through how 3 root 2 plus 4 times 3 root 2 minus 4 ended up giving us 18 minus 16, which simplifies to 2, and then I was able to simplify the whole fraction by removing a factor of 2 from the numerator and the denominator. Let's take a look at another example. The conjugate of our denominator here is going to be root 3 minus root 5. So I'm going to multiply by root 3 minus root 5 over root 3 minus root 5. Remember, this thing in green is just a version of 1 because we are creating equivalent fractions. When I multiply everything out, my numerator gets very messy, but my denominator, you'll notice, ends up just being, as we said up here, if we do a plus b times a minus b, we get a squared minus b squared. Well, we have root 3 plus root 5 times root 3 minus root 5. So we're going to get root 3 squared minus root 5 squared, which is 3 minus 5. Okay. We had to use FOIL to multiply out everything on the top. And this guy is going to simplify to this fraction. The top is pretty gnarly, yes, but the denominator no longer has radicals in it, and that was our goal. That is the end of section 1.5. I know it was a really tough section. If you want to and review some sections of this video, I highly recommend it. All right, good luck.